There's something peculiar about distance in the universe, something that challenges everything we think we know about how things move apart. When you stand on one side of a room and a friend stands on the other, the space between you is simple, fixed, measurable. If your friend walks away, they're moving through that space, crossing it, their feet carrying them across the floor. The distance changes because they change position. This is motion as we understand it, as we experience it every moment of our lives. But when astronomers look out at distant galaxies and watch them grow farther away, something fundamentally different is happening. Those galaxies aren't traveling through space the way your friend crosses a room. They're not burning fuel, not pushing against anything, not moving in the way we typically understand motion. Instead, the space between us and those galaxies is stretching, expanding, growing. The galaxies are, in a very real sense, standing still while the fabric of the universe itself changes beneath them. This is one of the most profound and strange discoveries in the history of science. The universe is expanding, not into anything, not because things are flying apart from some central explosion, but because space itself, the stage on which cosmic events unfold, is growing larger. When we say the universe is expanding, we're not speaking metaphorically. We're describing a physical process that's happening right now, has been happening for nearly 14 billion years, and will continue happening into the unimaginable future. Every second, galaxies that aren't bound together by gravity grow a little farther apart. Every moment, the cosmos becomes a slightly larger version of itself. This expansion isn't something we can feel or see in our daily lives. The room you're in isn't getting bigger. The Earth isn't swelling. Our galaxy, the Milky Way, maintains its shape and size. Expansion operates only on the largest scales, where gravity's grip loosens and the fundamental nature of space asserts itself. It's a cosmic phenomenon, visible only when we look out across millions and billions of light years, watching the universe reveal its deepest nature. Understanding what expansion really means requires us to let go of our everyday intuitions about motion and distance. It demands that we think about space not as an empty container, passive and unchanging, but as something dynamic, something that can stretch and warp and carry everything along with it. It's a journey into one of the most beautiful and bewildering aspects of modern cosmology, a journey that begins with careful observations of light from distant galaxies and ends with questions about the ultimate fate of everything that exists. Tonight, we're going to explore this expansion together. We'll trace its discovery, understand what it means for space to stretch, meet the mysterious force that's making expansion accelerate, and contemplate what it all means for our place in an ever-growing cosmos. We'll move slowly through these ideas, letting them settle, making the abstract concrete. Because when you understand cosmic expansion, you're understanding something fundamental about the nature of reality itself. You're grasping why the universe looks the way it does, why it has the history it has, and what the far future holds. You're seeing the universe not as a static backdrop, but as something alive with change, eternally becoming something new. So let's begin this journey into the expanding cosmos, where distance itself is fluid, where space has a texture that can stretch, and where the most distant galaxies are carried away from us by forces that still puzzle the brightest minds in physics. Let's understand how space itself expands. Before we can truly grasp the expansion of the universe, we need to clear away a common misconception, one that even many scientifically literate people hold. When we hear that galaxies are moving away from us, our minds naturally picture those galaxies as objects flying through space, like stones thrown outward from some central point. We imagine them as travelers making a journey, crossing the vastness of space the way a ship crosses an ocean. This picture is wrong, or at least deeply incomplete. The expansion of the universe is not galaxies moving through space. It is space itself stretching, with galaxies embedded in that space like raisins in rising bread dough. This distinction might seem subtle, even semantic, but it's actually crucial to understanding what's really happening in the cosmos. Imagine you're making a loaf of raisin bread. You've mixed the dough and scattered raisins throughout it, and now you place it in the oven to bake. As the dough rises, something interesting happens. Every raisin moves farther away from every other raisin. Not because the raisins themselves are moving through the dough, but because the dough between them is expanding. A raisin near one edge of the loaf looks around and sees all the other raisins receding from it. A raisin in the middle sees the exact same thing. There's no center to the expansion from the raisin's perspective. Every raisin is equally justified in thinking of itself as stationary while all the others move away. This is remarkably similar to what happens in the universe. Galaxies are embedded in the fabric of space like raisins in dough. As space expands, every galaxy finds itself getting farther from every other galaxy, on average. And here's the crucial part. From any galaxy's perspective, it looks like all the other galaxies are moving away from it. There's no special location, no center of the universe from which everything is fleeing. Every point in space experiences the expansion in the same way. The technical term for this is that expansion is homogeneous and isotropic. Homogeneous means it's the same everywhere. No matter where you are in the universe, you'll see the same general pattern. Distant galaxies receding, with more distant ones receding faster. Now, let's make this more concrete with actual numbers. When we observe a galaxy 100 million light-years away, we might find it's receding from us at about 7,000 kilometers per second. A galaxy 200 million light-years away recedes at about 14,000 kilometers per second. The relationship is linear. Twice the distance means twice the recession speed. This is Hubble's law, named after the astronomer Edwin Hubble, though we'll meet him properly in just a moment. But here's where things get truly strange. What happens when we look at galaxies so far away that this linear relationship predicts recession speeds faster than light? According to Einstein's special relativity, nothing can move through space faster than light. Does the universe grind to a halt at some maximum distance? Does something prevent galaxies from receding faster than light speed? No. And this is where the distinction between moving through space and space itself expanding becomes absolutely critical. Special relativity's speed limit applies to objects moving through space, to local motion within a region. It doesn't constrain what space itself can do. There's no law of physics preventing space from expanding such that two very distant points recede from each other faster than light. In fact, the most distant observable galaxies are, right now, receding from us at several times the speed of light. This doesn't violate relativity because they're not moving through space at that speed. The space between us and them is growing. Think of it this way. If you draw two dots on a rubber band and then stretch the rubber band, the dots move apart. They're stationary on the rubber while the rubber itself stretches. If you stretch the rubber fast enough or make it long enough, the dots can separate faster than any speed limit you impose on things moving along the rubber's surface. Now, you might wonder, if space is expanding everywhere, why isn't everything expanding? Why doesn't your body expand, or the Earth, or our solar system, or our galaxy? The answer is gravity, and it's worth understanding clearly. Expansion is incredibly gentle on small scales. The current expansion rate is characterized by the Hubble constant, currently measured at about 70 kilometers per second per megaparsec. A megaparsec is 3.26 million light-years. So if you have 2 points in space separated by 3.26 million light-years, with nothing holding them together, space's expansion will make them recede from each other at 70 kilometers per second. But gravity holds things together. The Earth orbits the Sun because gravity's pull is enormously stronger than the expansion of space at that scale. Even the Milky Way and Andromeda galaxies are gravitationally bound to each other, part of what's called the local group of galaxies. Within this group, gravity overwhelms expansion. The galaxies aren't being carried apart by cosmic expansion. They're dancing around each other, with Andromeda actually approaching us for an eventual collision in about 4 billion years. It's only when we look beyond our local group, beyond the region where gravity holds structures together, that we see the clear signature of cosmic expansion. Out there, where galaxies are separated by tens and hundreds of millions of light years, where gravity's grip weakens with distance, expansion dominates, space stretches, distances grow, the universe becomes a larger version of itself. There's something almost musical about this balance. At small scales, gravity conducts the orchestra, keeping stars in galaxies, galaxies in groups, creating structure and form. At large scales, expansion takes over, stretching space, carrying distant structures away from each other. And this expansion is not slowing down. This is one of the great surprises of modern cosmology, something we'll explore in detail soon. For now, it's enough to know that the universe's expansion is actually accelerating. Some mysterious component, which we call dark energy, is causing space to stretch faster and faster as time goes on. The implications of this are profound and strange. But let's not get ahead of ourselves. To truly understand expansion, to grasp where this knowledge comes from and what it means, we need to go back to the beginning of the story. We need to meet the people who first saw the expanding universe in the light from distant galaxies. We need to understand how patient observation and careful measurement revealed one of the most important truths about the cosmos. We need to meet Edwin Hubble and witness the discovery that changed everything. In the early decades of the 20th century, humanity's understanding of the universe was about to undergo a revolution. But in those years before the revolution, astronomers thought they knew the cosmos fairly well. The Milky Way galaxy, they believed, was the entire universe. Those fuzzy patches of light visible through telescopes, the so-called spiral nebulae, were clouds of gas and dust within our own galaxy, perhaps places where new stars were forming. The universe was static, eternal, and comprehensively understood, or so they thought. The seeds of revolution were planted by people whose names are less famous than they deserve to be. One of them was Henrietta Swan Leavitt, a woman working at Harvard College Observatory in the early 1900s. Leavitt's job was to examine photographic plates of the night sky, cataloging and measuring stars. It was painstaking work, often tedious, the kind of labor that the astronomical establishment considered suitable for women, but beneath the dignity of male astronomers. But Leavitt made a discovery that would change astronomy forever. She studied a class of stars called Cepheid variables, stars whose brightness fluctuates in a regular, predictable pattern. Some Cepheids pulse over days, others over weeks, their light swelling and dimming like cosmic heartbeats. What Leavitt discovered, through meticulous observation and analysis, was a relationship between a Cepheid's period and its intrinsic luminosity. Cepheids that pulsed slowly were intrinsically brighter than those that pulsed quickly. The period told you the star's actual brightness. This was revolutionary because it gave astronomers a way to measure cosmic distances. If you observe a Cepheid and measure its period, you know its intrinsic brightness. If you then measure how bright it appears from Earth, you can calculate how far away it must be. Brighter objects that appear dim must be far away. Dimmer objects that appear bright must be close. It's simple geometry, but it required Leavitt's period luminosity relationship to work. Cepheids became standard candles, objects of known brightness that could be used to measure the vast distances of space. And this is where Edwin Hubble enters our story. Hubble was a complex man. a former athlete and lawyer who turned to astronomy and became one of the most important observers in the history of the field. He worked at Mount Wilson Observatory in California, home to the most powerful telescope in the world at the time, the 100-inch Hooker telescope. This massive instrument could see farther and more clearly than anything that had come before. And Hubble used it to peer at those mysterious spiral nebulae. In 1924, Hubble made an observation that shattered the prevailing view of the universe. He identified Cepheid variable stars in the Andromeda Nebula. Using Leavitt's period luminosity relationship, he calculated their distance. The result was staggering. Andromeda was approximately 900,000 light-years away, though we now know the true distance is about 2.5 million light-years, as Hubble's early distance measurements underestimated cosmic distances. Even so, his measurement was far beyond the known boundaries of the Milky Way. Andromeda wasn't a cloud of gas within our galaxy. It was a galaxy itself, a separate island universe containing hundreds of billions of stars. The universe was suddenly, incomprehensibly larger than anyone had imagined. The Milky Way was just one galaxy among countless others scattered through space. But Hubble wasn't finished. Over the next few years, he identified more distant galaxies and measured their distances using Cepheids and other methods. And he noticed something else. Something that another astronomer had already begun to document. Vesto Slipher, working at Lowell Observatory in Arizona, had been studying the light from spiral nebulae since around 1912. He used spectroscopy, a technique that splits light into its component wavelengths, creating a spectrum. Every element produces characteristic patterns in a spectrum, specific wavelengths, where it emits or absorbs light. Slipher noticed that the spectral lines from most spiral nebulae were shifted toward the red end of the spectrum, toward longer wavelengths. This redshift was puzzling. The most natural interpretation was the Doppler effect, the same phenomenon that makes an ambulance siren sound higher pitched as it approaches and lower pitched as it recedes. Light from an object moving away from us gets stretched to longer wavelengths, shifting toward the red. Slipher's observations suggested that most spiral nebulae were moving away from us, many at tremendous speeds. By the late 1920 seconds, Hubble had distances to many galaxies, and Slipher had velocity measurements from their redshifts. Hubble began comparing the two. He plotted galaxy distances on one axis and recession velocities on the other. What emerged was one of the most important graphs in the history of astronomy. The galaxies fell along a line. The farther away a galaxy was, the faster it was receding. The relationship was linear, simple, elegant, and completely unexpected. On the 15th of March, 1929, Hubble published his results in the Proceedings of the National Academy of Sciences. The paper was just 6 pages long, remarkably brief for such a momentous discovery. But those 6 pages contained a revelation. The universe was expanding. Now, to be completely accurate, Hubble himself was cautious about the interpretation. He presented the velocity-distance relationship as an empirical finding, a pattern in the data. He knew that interpreting the redshifts as real motion through space raised theoretical issues, but the implication was clear to anyone familiar with the theoretical work that had been developing alongside these observations. Albert Einstein's general theory of relativity, published in 1915, described gravity not as a force, but as a curvature of space-time caused by mass and energy. When physicists applied general relativity to the universe as a whole, they found that the equations didn't naturally produce a static universe. The simplest solutions described a universe that was either expanding or contracting. Einstein himself found this disturbing. Like everyone else at the time, he believed the universe was eternal and unchanging. So he modified his equations, adding a term called the cosmological constant that could counterbalance gravity and produce a static universe. It was an ugly fix, what we might call a fudge factor, but it seemed necessary to match what Einstein thought reality must be. In 1922, a Russian mathematician named Alexander Friedman showed that Einstein's static universe was unstable, like a pencil balanced on its point. The slightest perturbation would cause it to either expand or contract. Friedman proposed models of expanding universes, solutions to Einstein's equations that described cosmic growth. Then, in 1927, Georges Lemaitre, a Belgian priest and physicist, independently derived similar solutions and went further. He connected the theoretical predictions to actual observations, noting that if the universe was expanding, distant galaxies should show redshifts proportional to their distances. He even calculated a value for what would become known as the Hubble constant 2 years before Hubble's publication. Lemaitre's work was published in a Belgian journal and initially went unnoticed by most astronomers. But when Hubble's observational confirmation came in 1929, the theoretical framework was ready and waiting. The universe was expanding, just as general relativity predicted. Einstein visited Mount Wilson Observatory in 1931 to see Hubble's work firsthand. By this time, Einstein had abandoned the cosmological constant. According to physicist George Gamow's later recollection, Einstein called it his greatest blunder. Though some historians debate whether Einstein used those exact words, regardless of the precise phrasing, Einstein recognized that the universe wasn't static after all. It was dynamic, growing, evolving. Observations had forced a profound shift in our cosmic understanding. Now, it's worth noting that Hubble's original measurements were quite wrong in absolute terms. His distances were too small, by a factor of about 7. This happened because the methods for measuring cosmic distances were still being refined, and some of the objects he used as standard candles weren't actually as standard as he thought. But here's the beautiful thing. Even though his distances were wrong, the relationship held. More distant galaxies really did recede faster. The linear pattern was real. As measurement techniques improved over the following decades, the distances got corrected, the expansion rate got refined, but the fundamental discovery remained solid. The universe expands. This expansion pointed backward to a profound implication. If galaxies are moving apart now, they must have been closer together in the past. Wind the clock back far enough, and all the matter and energy in the universe must have been compressed into an incredibly dense, hot state. This was the seed of what we now call the Big Bang Theory, though that name wouldn't be coined until the late 1940 seconds. Lemaitre called it the primeval atom, imagining the universe beginning in an unimaginably dense point that exploded outward, with the expansion we see today being the continuing aftermath of that ancient eruption. Many scientists preferred models of a universe that had always existed in more or less its current form. But as evidence accumulated, particularly with the discovery of the cosmic microwave background radiation in 1965, the Big Bang Theory became the standard model of cosmology. Hubble's discovery gave the universe a history. It transformed cosmology from a field of philosophical speculation into a science based on observation and measurement, and it opened up new questions, profound questions that we're still working to answer. How fast is the universe expanding? Has the expansion rate changed over cosmic history? What's driving the expansion? Will it continue forever? These questions drive modern cosmology, and to answer them, we need to understand how astronomers actually measure cosmic expansion, how they read the history of the universe in the light from distant galaxies. Let's look at how we decode the expanding cosmos. Light is the messenger that brings us news from the cosmos. Every photon that reaches our telescopes has traveled across space, sometimes for billions of years, carrying information encoded in its wavelength and energy. When we learn to read this information correctly, we can measure distances that dwarf human comprehension and trace the expansion of the universe itself. The key to reading cosmic expansion is redshift, that shift of light toward longer wavelengths that Vesto Slipher first noticed in the spectra of distant galaxies. Understanding redshift means understanding how expansion affects light, and it requires us to think carefully about what's actually happening to photons as they traverse expanding space. When a galaxy emits light, that light has specific wavelengths determined by the atomic processes happening in the galaxy's stars and gas. Hydrogen, for instance, produces a characteristic pattern of spectral lines, specific wavelengths where it absorbs or emits light. These wavelengths are determined by the physics of hydrogen atoms, and they're the same everywhere in the universe. But when we observe light from a distant galaxy, we find that these spectral lines aren't at the wavelengths we expect. A line that should appear in the blue part of the spectrum might show up in the green. One that should be in the ultraviolet might appear in the visible range. The entire spectrum is stretched. This is cosmological redshift, and while it's often explained as being like the Doppler effect, the underlying cause is actually quite different. The Doppler effect happens when a source moves through space toward or away from an observer, compressing or stretching the waves it emits. You hear this every time an ambulance passes you on the street, the pitch of its siren dropping as it moves away. Cosmological redshift, however, is caused by the expansion of space itself. As a photon travels from a distant galaxy to us, space is expanding. The expansion stretches the photon's wavelength along with it, like a wave drawn on a rubber band that gets longer as the band is stretched. By the time the photon reaches us, its wavelength has been stretched in proportion to how much the universe has expanded during its journey. Mathematically, we describe redshift with the letter Z. If a spectral line that should have a wavelength of 500 nanometers is observed at 600 nanometers, the redshift Z equals 0.2. This means the universe has expanded by 20% since that light was emitted. A redshift of 1 means the universe has doubled in size. A redshift of 2 means it's tripled. The most distant galaxies we've observed have redshifts of 10 or more, meaning the universe has expanded more than tenfold since their light began its journey to us. Measuring redshift is relatively straightforward with modern instruments. Astronomers use spectrographs attached to telescopes to split the light from a galaxy into its component wavelengths. They identify the characteristic patterns of known elements and measure how far those patterns have shifted from their rest wavelengths. The precision can be remarkable. Modern instruments can measure redshifts to several decimal places, detecting expansion that occurred with exquisite precision. But redshift alone doesn't tell us distance. It tells us how much the universe has expanded since the light was emitted, which is related to but not the same as distance. To convert redshift to distance, we need to know how the expansion rate has changed over cosmic history, and that requires understanding the Hubble constant. The Hubble constant, usually written as H0, pronounced H0, describes the current rate of cosmic expansion. It's typically expressed in units of kilometers per second per megaparsec. The current best measurements put it around 70 kilometers per second per megaparsec, though there's an interesting tension we'll discuss in a moment. What this means is that for every megaparsec of distance, about 3.26 million light-years, the recession velocity increases by about 70 kilometers per second. A galaxy 10 megaparsecs away recedes at 700 kilometers per second. One 100 megaparsecs away recedes at 7,000 kilometers per second. The relationship scales linearly for relatively nearby galaxies. But measuring the Hubble constant is fiendishly difficult. It requires knowing both the distance to galaxies and their recession velocities with high precision. The distances are the hard part. For nearby galaxies, astronomers use the same technique Hubble pioneered: Cepheid variable stars. Find Cepheids in a distant galaxy, measure their periods, calculate their intrinsic luminosities using Leavitt's relationship, compare to their apparent brightness, and derive the distance. The Hubble Space Telescope, with its sharp vision, can detect Cepheids in galaxies tens of millions of light-years away. For more distant galaxies, astronomers use Type Ia supernovae. These are exploding stars that reach approximately the same peak brightness because they result from white dwarf stars that collapse when they reach a specific mass limit. Observe a Type Ia supernova, measure its peak brightness, and you can calculate its distance. These supernovae are bright enough to be seen billions of light-years away, making them crucial tools for measuring cosmic distances. There are other methods too. The brightness of certain types of galaxies, the properties of galaxy clusters, subtle patterns in the distribution of matter called baryon acoustic oscillations. Each method has its strengths and weaknesses, its systematic uncertainties and potential errors. And here's where things get interesting and a bit troubling. Different methods of measuring the Hubble constant are giving different answers. This is called the Hubble tension, and it's one of the most important unsolved problems in modern cosmology. Measurements using Cepheids and Type Ia supernovae, looking at relatively nearby parts of the universe, give a Hubble constant of about 73 kilometers per second per megaparsec. Measurements using the cosmic microwave background, the afterglow of the Big Bang itself, combined with our understanding of how the universe evolved, give a value of about 67. The difference might seem small, but it's statistically significant. These measurements shouldn't disagree this much if our understanding of the universe is correct. The Hubble tension might mean there's something wrong with one of the measurement methods. Perhaps there are systematic errors we haven't accounted for. Or it might mean something more profound, that our standard model of cosmology is missing something important. Perhaps dark energy behaves differently than we think. Perhaps there's some other component to the universe we haven't discovered. Perhaps the expansion rate has changed in ways we don't expect. Resolving the Hubble tension is a major goal of observational cosmology right now. New surveys are mapping the distribution of galaxies with unprecedented detail. Each observation refines our understanding, and each raises new questions. But even with the tension, even with the uncertainties, the fundamental picture is clear. The universe is expanding at a rate of roughly 70 kilometers per second per megaparsec. This expansion carries distant galaxies away from us, stretching the light they emit, creating the redshifts we observe. And from these redshifts, from these careful measurements of light that has traveled across billions of light years of expanding space, we can reconstruct the history of cosmic expansion. We can determine when the universe was smaller, denser. That history reveals something profound and unexpected. The expansion of the universe hasn't been constant. For the first several billion years, gravity was winning, slowing the expansion down. But then something changed. About 5 billion years ago, a mysterious component took over, and expansion began to accelerate. That mysterious component is what we call dark energy, and it's one of the deepest mysteries in all of physics. Through the 1,990 seconds, cosmologists had a clear expectation about the universe's expansion. It should be slowing down. This made perfect sense based on everything they knew about gravity and the content of the universe. Think about throwing a ball upward. Gravity pulls on the ball, slowing its ascent. The ball might escape Earth's gravity if you throw it fast enough, but even then, it's still slowing down, just not enough to fall back. Cosmologists expected something similar for the universe. All the matter and energy in the universe exerts gravitational attraction, pulling everything toward everything else. This should act as a brake on expansion, slowing it down over time. The question was how much it was slowing. If there was enough matter in the universe, gravity might eventually halt the expansion and reverse it. leading to a big crunch where everything collapses back to a point. If there wasn't enough matter, expansion would continue forever, but at an ever-decreasing rate. Finding out which scenario described our universe required measuring how the expansion rate had changed over cosmic history. Two teams of astronomers set out to make this measurement in the 1,990 seconds. The Supernova Cosmology Project, led by Saul Perlmutter, and the High-Z Supernova Search Team, led by Brian Schmidt and Adam Rees. Both teams use the same basic approach. Observe very distant Type Ia supernovae, measure their redshifts and distances, and compare to what you'd expect for different expansion histories. Type Ia supernovae are ideal for this work because they're extremely bright, visible across billions of light years, and they reach approximately the same peak luminosity. This makes them excellent standard candles for measuring cosmic distances. The teams searched for these supernovae in distant galaxies, catching them in the act of exploding, measuring their brightnesses and spectra. The expectation was clear. If expansion was slowing down, distant supernovae should appear brighter than they would in a universe expanding at a constant rate, because deceleration would mean they're closer than constant expansion would predict. The only question was how much brighter. In 1998, both teams announced their results, and what they found shocked the physics world. The distant supernovae were dimmer than expected. Not brighter, dimmer. This meant they were farther away than they should be if expansion had been slowing down. The only way to make sense of this was if expansion had been speeding up. Somewhere in the universe's history, expansion transitioned from decelerating to accelerating. The universe's expansion is accelerating. This news rippled through the scientific community like a thunderclap. It went against all expectations. What could possibly cause expansion to speed up? What force could counteract gravity's pull and actually push space to expand faster? The answer, frustratingly, is that we don't know. Dark energy is the term we use for whatever is causing the accelerating expansion. It's not an explanation. It's a placeholder, a label for a mystery. We know dark energy exists because we see its effects. The accelerating expansion, the dimmer than expected supernovae, patterns in the cosmic microwave background, and the distribution of galaxies. But we don't know what it is. The discovery earned Perlmutter, Schmidt, and Rees the 2011 Nobel Prize in Physics. Their work revealed that the universe is dominated by something completely unexpected, something that behaves unlike anything else we know about. So what could dark energy be? Scientists have proposed several possibilities, and it's worth understanding the leading candidates. The most popular explanation is that dark energy is the cosmological constant, that same term Einstein added to his equations to create a static universe and later abandoned. But the cosmological constant has been reborn with a new interpretation. Instead of a fudge factor, it's now understood as representing vacuum energy, the energy of empty space itself. Quantum field theory, the framework that describes subatomic particles and forces, predicts that even empty space isn't truly empty. Particles and antiparticles constantly pop into existence and annihilate in fleeting moments, creating a background energy that pervades all of space. This vacuum energy would have a peculiar property. Unlike matter, which dilutes as space expands, vacuum energy has constant density. As the universe grows and more space comes into existence, more vacuum energy appears, maintaining the same energy density everywhere and at all times. This constant energy density would exert what we can think of as a negative pressure, a kind of anti-gravity that pushes space apart rather than pulling it together. The larger the universe gets, the more total vacuum energy it contains, and the stronger this repulsive effect becomes. This could explain why expansion is accelerating. There's just one problem with this explanation. When physicists calculate how much vacuum energy there should be based on quantum field theory, they get an answer that's wrong by a factor of about 10 to the power of 120. That's a 1 followed by 120 zeros. It's possibly the worst prediction in the history of physics. The energy density we observe for dark energy is incredibly small, about 6 times 10 to the negative 30th grams per cubic centimeter. But quantum field theory predicts it should be vastly, incomprehensibly larger. Why the actual value is so much smaller is called the cosmological constant problem, and nobody has solved it. Despite this massive theoretical problem, the cosmological constant remains the leading explanation for dark energy because it fits observations so well. When we measure how dark energy behaves, how its density changes over cosmic time, the answer we get is consistent with it being constant, unchanging, the same in the early universe as it is today. But there are alternatives. Some physicists propose that dark energy isn't a constant at all, but a dynamic field that changes over time and space, something called quintessence. This would be a new fundamental field, similar in some ways to the Higgs field that gives particles mass, but with different properties. Quintessence could vary in strength, potentially explaining some features of cosmic expansion that a pure cosmological constant struggles with. Recent observations from the Dark Energy Spectroscopic Instrument, DESI, have hinted at something intriguing. When DESI's data on baryon acoustic oscillations is combined with other measurements, there's a slight preference for dark energy that changes over time rather than remaining constant. The statistical significance isn't strong enough to claim a discovery, but it's enough to make theorists pay attention. If confirmed, it would mean dark energy is even stranger than we thought. Another possibility is that there's something wrong with our theory of gravity itself. General relativity has passed every test we've thrown at it on scales ranging from laboratory experiments to the orbits of planets to the dance of black holes. But maybe, just maybe, it breaks down on the largest cosmic scales. Maybe gravity behaves differently across billions of light years than Einstein predicted. Modified gravity theories can potentially explain cosmic acceleration without invoking dark energy at all. The detection of gravitational waves in 2015 and subsequent observations have constrained some modified gravity theories. Gravitational waves travel at the speed of light, just as general relativity predicts, ruling out some alternative theories. But many modified gravity proposals remain viable. So, where does this leave us? We live in a universe dominated by something we don't understand. Current measurements suggest that dark energy makes up about 68% of the total energy content of the universe. Dark matter, another mysterious component we can only detect through its gravitational effects, accounts for about 27%. Ordinary matter, the atoms that make up stars and planets and us, contributes a mere 5%. We are a tiny minority in a universe dominated by darkness. Multiple missions are working to better characterize dark energy. The European Space Agency's Euclid satellite, launched in 2023, is mapping the distribution of galaxies across cosmic time. NASA's Nancy Grace Roman Space Telescope, scheduled for launch by 2027, will conduct detailed surveys of supernovae and galaxy clustering. The Vera Rubin Observatory in Chile will begin operations soon, scanning the sky repeatedly to catch transient events and map cosmic structure. These instruments will measure how dark energy has behaved over the universe's history with unprecedented precision. They'll tell us whether it's truly constant or whether it changes. They'll constrain its properties and perhaps point toward its nature. But even with this wealth of data, understanding what dark energy actually is may require breakthroughs in fundamental physics. For now, we live with the mystery. We know the universe is expanding faster and faster. We know this acceleration began about 5 billion years ago, when dark energy's repulsive effect overcame matter's gravitational pull. We know this acceleration will continue, shaping the far future of the cosmos in profound ways. But we don't know why. We don't know what dark energy is, where it comes from, or what it means for the fundamental laws of physics. It's humbling, really. After centuries of scientific progress, we find that we don't understand what most of the universe is made of or what force is determining its ultimate fate. Yet, this ignorance is also exciting. Somewhere in the mystery of dark energy lies a clue to deeper truths about the nature of space, time, and existence itself. Solving this mystery might revolutionize physics as profoundly as quantum mechanics or relativity did in the last century. For now, though, dark energy remains what its name suggests: dark, mysterious, seen only through its effects on the expanding cosmos. And that expansion has a history, a story that stretches from the earliest moments of time to the present day and beyond. Let's trace that history now, watching how the universe has grown and changed over nearly 14 billion years. The universe has not always expanded at the same rate. Its history is one of dramatic changes, of eras when different forces dominated, of transitions that fundamentally altered the cosmos. To understand expansion, we need to trace this history from the beginning. In the very first moments after the Big Bang, something extraordinary happened. During the tiniest fraction of a second, starting about 10 to the minus 35 seconds after time began, the universe underwent a period of exponential expansion called cosmic inflation. In a time interval almost too brief to comprehend, space expanded by a factor of at least 10 to the 26, perhaps vastly more. This inflationary period was driven by a hypothetical field called the inflaton, which existed in a high-energy state. The physics of this field caused space itself to expand at an accelerating rate, doubling in size many times over in rapid succession. In less than a trillionth of a second, a region smaller than a proton expanded to perhaps the size of a grapefruit or larger. Why do cosmologists think this happened? Inflation solves several problems that plague simpler Big Bang models. One is the horizon problem. The universe appears remarkably uniform in all directions, with the same temperature and density everywhere we look on large scales. But in a universe that expanded at a more sedate rate, regions on opposite sides of the sky would never have been in contact with each other, never had time to equilibrate to the same temperature. How did they end up so similar? Inflation answers this. If all the observable universe we see today started out as a tiny region, small enough that every part was in contact with every other part, it could have equilibrated before inflation blew it up to cosmic scales. The uniformity we see is the result of that early contact, preserved and magnified by inflation. Inflation also solves the flatness problem. The geometry of space can be curved, like the surface of a sphere or a saddle. Our universe appears to be very close to flat, like an infinite plane, but slight deviations from flatness would have been magnified over time unless the universe started out extremely, precisely flat. Inflation explains this. If you inflate a balloon enough, any small patch of its surface looks flat. Inflate the universe by a factor of 10 to the 26 or more, and any initial curvature gets stretched nearly flat. Perhaps most importantly, inflation provides a mechanism for generating the tiny density fluctuations that eventually grew into galaxies, clusters, and all cosmic structure. Quantum fluctuations in the inflaton field, blown up to cosmic scales by inflation, created regions that were slightly denser or less dense than average. Gravity later amplified these fluctuations, pulling matter toward the denser regions, creating the cosmic web of galaxies we see today. After inflation ended, the universe transitioned to a more leisurely expansion. The energy that drove inflation decayed into a hot soup of particles and radiation. For the next several 100,000 years, the universe was dominated by radiation, by light, and other massless or near-massless particles. During this radiation-dominated era, the universe expanded and cooled, but expansion was decelerating, slowed by the gravity of all that energy. As the universe expanded, radiation cooled and diluted faster than matter did. This is because radiation's energy decreases as its wavelength stretches with expansion, while matter just becomes more spread out. Eventually, around 50,000 years after the Big Bang, the energy density of matter surpassed that of radiation. The universe entered the matter-dominated era. For billions of years, matter dominated the universe's dynamics. Gravity pulled matter together, forming the first stars, the first galaxies, the first clusters. But gravity also acted as a brake on cosmic expansion, slowing it down. The expansion rate decreased over time, though it never stopped entirely. This makes intuitive sense. All the matter in the universe exerts gravitational pull on all the other matter. This pull opposes expansion, slowing it down. If there had been enough matter, this gravitational braking might eventually have halted expansion and reversed it. But there wasn't enough. Expansion continued, albeit at a decreasing rate. Then, roughly 5 billion years ago, something shifted. Meanwhile, if dark energy is indeed the cosmological constant, its density remained unchanged. With matter diluting and dark energy staying constant, there came a point when dark energy's density exceeded matter's density. And when that happened, dark energy took over. Its repulsive effect began to dominate over matter's gravitational pull. Expansion stopped decelerating and began to accelerate. This is the transition that the supernova observations revealed, the moment when the universe's fate shifted from gradually slowing expansion to runaway acceleration. We can see this history written in the cosmic microwave background, the faint afterglow of the Big Bang that fills all of space. This radiation was released about 380,000 years after the Big Bang, when the universe cooled enough for electrons and protons to combine into neutral hydrogen atoms. Before this, the universe was opaque, a plasma of charged particles that scattered light. After this recombination, the universe became transparent, and light could travel freely. That first free light is what we see as the cosmic microwave background. It's been stretched by expansion from visible light to microwaves, redshifted by a factor of about 1,100. When we observe it with precision instruments like the Wilkinson Microwave Anisotropy Probe or the Planck satellite, we see tiny temperature variations, patterns that encode information about the universe's composition and history. These patterns tell us how much ordinary matter, and dark energy the universe contains. They tell us the geometry of space and the initial conditions from which all structure grew. They provide some of the strongest evidence for the standard cosmological model and for the existence of dark energy. We can also trace expansion history by looking at galaxies at different distances, which is the same as looking at different times in the past. Light takes time to travel. So when we observe a galaxy 10 billion light years away, we're seeing it as it was 10 billion years ago. By measuring how galaxies at different distances are distributed and how they cluster, we can reconstruct how the universe has evolved. These observations paint a consistent picture. In the early universe, expansion was rapid, driven first by inflation and then decelerating under matter and radiation's gravity. For billions of years, structure grew as matter clumped together. Galaxies formed, merged, evolved, stars were born, lived, died, and then, as the universe matured, dark energy began its takeover. Expansion started to accelerate. This acceleration is still gentle on cosmic terms, but it's relentless. Every second, every moment, the rate of expansion increases slightly. In the far future, this acceleration will have profound consequences. The expansion history of the universe is not a simple story of steady growth. From the explosive inflation of the earliest moments, to the decelerating expansion of the matter-dominated era, to the current accelerating expansion driven by dark energy, the universe has undergone fundamental transformations. And understanding this history helps us understand what comes next. Because if dark energy continues to dominate, if acceleration continues, the universe's future looks very different from its past. Before we explore that future, though, we need to understand another consequence of expansion: the existence of horizons, boundaries beyond which we cannot see, limits to what the universe allows us to know. Expansion creates boundaries, not physical walls but limits to observation and knowledge. These cosmic horizons are among the most profound consequences of living in an expanding universe, and they deserve our careful attention. The most straightforward horizon is the particle horizon, which defines the observable universe. This is the boundary between the region from which light has had time to reach us and the region from which it hasn't. Light travels at a finite speed, about 300,000 kilometers per second. The universe is about 13.8 billion years old. You might think this means we can see objects up to 13.8 billion light years away, that the observable universe has a radius of 13.8 billion light years. But expansion complicates this calculation considerably. When light left a distant galaxy billions of years ago, that galaxy was closer to us than it is now. As the light traveled through space, space itself was expanding, stretching the distance the light had to cover. Furthermore, the galaxy that emitted the light has been carried farther away by expansion during the light's journey. When cosmologists properly account for expansion, they find that the radius of the observable universe is about 46.5 billion light years. Objects that are now this far away emitted light that, after traveling through expanding space for 13.8 billion years, is just reaching us now. This is our particle horizon. Everything within this spherical volume of 46.5 billion light-year radius is potentially observable. We can, in principle, receive light from events that happen there. Everything beyond is causally disconnected from us. Light from those regions hasn't had time to reach us yet. But here's something beautiful and a bit melancholy. The particle horizon is expanding. As time passes, light from more distant regions reaches us. The observable universe grows. In that sense, we're constantly seeing new parts of the cosmos for the first time. However, there's another horizon that tells a darker story: the cosmic event horizon. The event horizon defines the boundary between regions we can ever observe and regions we can never observe, even if we wait forever. This horizon exists because of accelerating expansion. Imagine a galaxy that's currently just beyond some critical distance from us. Light leaving that galaxy right now will try to travel toward us, but space is expanding. If expansion is accelerating, there's a distance beyond which space expands so rapidly that light making the journey toward us never actually makes progress. The light tries to cross the expanding space, but space expands faster than the light can traverse it. This critical distance defines the cosmic event horizon. No signal from beyond that horizon, no light, no gravitational wave, no neutrino can ever reach us, no matter how long we wait. Currently, the cosmic event horizon is about 16 billion light years away. This is much closer than the particle horizon. There are galaxies we can see now, galaxies within our observable universe that are already beyond the event horizon. We see them as they were in the past, but what's happening to them now, we can never know. The light being emitted from those galaxies at this very moment will never reach us. This creates a strange situation. Over time, more and more galaxies will cross our event horizon. We'll still be able to see them for billions of years afterward, watching increasingly ancient light that left them before they crossed over. But eventually, that light will be so redshifted, so stretched by expansion, that it becomes undetectable. Galaxies will fade from view, disappearing into invisibility. The far future universe, if dark energy remains constant, will be a lonely place. All the galaxies beyond our local group will eventually vanish from the sky. Future astronomers, billions of years from now, might look up and see only their own galaxy and its close companions in an otherwise empty cosmos. There's also what's called the Hubble sphere, the distance at which the recession velocity equals the speed of light. This is different from both the particle horizon and the event horizon, and it's currently at about 4,200 megaparsecs, or roughly 14 billion light years. The Hubble sphere is interesting because it's a sort of boundary in perception. Objects beyond the Hubble sphere are receding faster than light, yet we can still see some of them because they're within our particle horizon. Light from these objects was emitted when they were closer, within the Hubble sphere, and that light is now reaching us, even though the objects themselves have been carried beyond the Hubble sphere by expansion. These horizons matter because they limit what we can learn about the universe. We can never directly observe what lies beyond our particle horizon. We can never send a signal to or receive one from beyond our event horizon. There could be an infinite universe beyond what we can see. This raises profound questions. Is the universe finite or infinite? If it's finite, what's beyond its edge? If it's infinite, are there other regions vastly different from ours, with different physical laws or different histories? Some cosmic inflation models predict a vast multiverse, with our observable universe being just one bubble in an infinite froth of bubbles, each potentially with different properties. Other models suggest a universe that's finite but unbounded, curved back on itself like the surface of a sphere, though much more subtle in its curvature. We might never know the answers to these questions with certainty. The horizons impose fundamental limits on observation, yet cosmologists continue to search for clues. Patterns in the cosmic microwave background might hint at the global topology of space. Careful measurements of expansion might reveal features that constrain the universe's overall structure. But expansion also offers a kind of window into the past that's unavailable in a static universe. Because light takes time to travel, and because we can see objects at many different distances, we're essentially looking at the universe's history directly. When we observe a galaxy 10 billion light years away, we see it as it was 10 billion years ago. We can watch galaxies at different cosmic epochs and trace how they've evolved over time. The cosmic microwave background is the ultimate historical snapshot. It shows us the universe as it was just 380,000 years after the Big Bang, the moment it became transparent. We can't see farther back in electromagnetic radiation, but we might in gravitational waves or neutrinos, which interacted less with the early universe's plasma and might carry information from even earlier moments. In a sense, the observable universe is a cosmic time machine. Look far enough in any direction, and you're looking into the deep past. The horizons tell us how far we can look, both in space and time. And those horizons, particularly the event horizon, are shrinking in a comoving sense. As dark energy drives acceleration, the event horizon converges to a fixed proper distance. In the far future, it will become increasingly small in terms of how much of the universe we can ever hope to observe. This might seem like a loss, a narrowing of cosmic perspective, but it also gives us a gift: the knowledge that we live in a special cosmic epoch, a time when the universe's history is still visible in the sky, when we can look out and see the vast majority of cosmic time spread before us. Future civilizations, if they exist, might not have this privilege. They might live in a universe where all evidence of the Big Bang has faded, where the cosmic microwave background is redshifted into undetectability, where the distant galaxies have vanished from view. They might struggle to understand their universe's origin and history because expansion has erased the evidence. We are fortunate. We can still see the cosmos in its full glory, still trace its history, from the earliest observable moments to the present. The horizons are there, the limits are real, but we haven't yet lost our view of the expanding universe's grand narrative. But what does that narrative tell us about the far future? If expansion continues to accelerate, if dark energy maintains its grip, what will the universe become over timescales that dwarf the current age of the cosmos? Let's look into that distant future and see what expansion has in store. If we could step outside of time and watch the universe evolve over billions and trillions of years, we would see a cosmos gradually emptying, structures dissolving, galaxies fading into isolation. The far future of an accelerating universe is not violent, not catastrophic in the explosive sense, but it is profoundly transformative. Let's start closer to home, cosmically speaking. Our local group of galaxies, including the Milky Way, Andromeda, and about 50 smaller galaxies, is gravitationally bound. Expansion doesn't affect us on these scales because gravity holds us together. In about 4 billion years, the Milky Way and Andromeda will collide and merge, eventually forming a single giant elliptical galaxy that astronomers have playfully nicknamed Milkomeda. This merger will be dramatic, involving close encounters between stars, the disruption of spiral arms, the formation of new stars from compressed gas clouds. But it won't be a collision in the violent sense. The distances between individual stars are so vast that stellar collisions will be exceedingly rare. Our sun, if it still exists, might be flung to a different part of the new galaxy. After this merger, the local group will settle into a relatively stable configuration. The combined galaxy will contain the mass of both progenitors, and that mass will hold the system together against expansion. We, or at least our local group, will remain a coherent structure. But beyond the local group, everything else is receding. The Virgo cluster, a massive collection of galaxies about 54 million light-years away, is already moving away from us. More distant structures, the great clusters and superclusters that mark the cosmic web, are receding faster. As billions of years pass and expansion accelerates, these distant galaxies will move farther and farther away. Their light will be increasingly redshifted, stretched to longer and longer wavelengths. Galaxies that are now visible in optical telescopes will fade into the infrared, then into the radio spectrum. Eventually, their light will be redshifted beyond any wavelength our instruments could detect. One by one, galaxies will disappear from view, not because they're destroyed or have stopped shining, but because their light is being stretched by expansion until it becomes undetectable. The night sky will gradually empty. Imagine an astronomer 100 billion years from now. If any astronomers exist, they look up and see only their local galaxy and perhaps a few nearby companions. The rest of the sky is dark, empty, devoid of the distant galaxies that we see scattered throughout space. The cosmic microwave background, that faint echo of the Big Bang, has been redshifted into oblivion. Its temperature dropped to near absolute zero. This future astronomer would have a very hard time figuring out the history of the universe. All the evidence we have for the Big Bang, for cosmic evolution, for the existence of dark energy, would be gone. They might conclude that the universe is just their galaxy, eternal and unchanging, with no evidence to suggest otherwise. This is a peculiar feature of accelerating expansion. It erases its own history. The very process that shapes the universe's evolution eventually destroys the evidence of that evolution. But let's go even farther into the future, trillions of years hence. By this time, stars will have largely exhausted their fuel. Star formation requires gas clouds to collapse and ignite fusion, but in an ever-expanding universe, gas becomes more and more dispersed. Eventually, star formation slows and stops. The last stars will burn out, leaving behind white dwarfs, neutron stars, and black holes. Galaxies will darken as their stars die. The universe will be populated by stellar remnants, cold and dark, with only occasional flickers of light when objects collide or matter falls into black holes. On even longer timescales, the very structure of matter might change. Protons, the building blocks of atomic nuclei, might eventually decay over inconceivable timescales. This is predicted by some grand unified theories of particle physics, though it's never been observed and remains highly speculative. If protons do decay, even the white dwarfs and neutron stars will eventually dissolve into radiation and lighter particles. Black holes will evaporate through Hawking radiation, a quantum process that allows them to slowly radiate energy and shrink over incredibly long timescales. A black hole with the mass of the Sun would take about 10 to the power of 67 years to evaporate. Supermassive black holes would take even longer, timescales so vast they beggar description. But eventually, even the black holes will be gone. The universe will be left with a thin soup of particles spread across ever-expanding space, growing colder and more dilute with every passing moment. This is sometimes called the heat death of the universe, the state of maximum entropy where no energy gradients exist to drive any process. It's a universe where nothing can happen because everything is in equilibrium, spread out uniformly, approaching absolute zero in temperature. And through all of this, expansion continues. Space stretches, carrying the sparse remnants of matter and energy farther and farther apart. If dark energy remains constant, this expansion will persist forever, making the universe larger and emptier without end. There are other possible futures, depending on what dark energy actually is. If dark energy strengthens over time, a scenario called phantom energy, expansion could accelerate so violently that it eventually tears apart bound structures. First, galaxy clusters would be ripped apart, then galaxies, then solar systems, then planets. This Big Rip scenario would end with space expanding so rapidly that the fabric of space-time itself might be torn apart. Alternatively, if dark energy is not a cosmological constant but a field that can change, it might weaken or even reverse. In principle, this could lead to a big crunch, where expansion stops and reverses, and the universe collapses back to a point. But current observations give no indication that this is likely. The most probable future, based on what we know now, is continued accelerating expansion into the heat death. It's not a violent end, not a dramatic finale. It's a slow fading, a gradual dispersal, the universe becoming ever more spread out, ever colder, ever darker, until finally reaching a state where nothing of significance can happen anymore. These timescales are so long that they're almost meaningless in human terms. 1 trillion years is already vastly longer than the current age of the universe. 10 to the 67th years is a number so large that it doesn't connect to any human experience. Yet this is the ultimate consequence of accelerating expansion. There's something both humbling and melancholy about this vision of the far future. The universe, which now seems so full of light and structure and dynamic activity, will eventually become a cold, empty void. The galaxies, stars, and planets that exist now are temporary structures, islands of complexity in a cosmos that's inexorably moving toward simplicity and stillness. Yet there's also a kind of beauty in this impermanence. The universe is not static, not unchanging. It's a dynamic system with a history and a future. We happen to exist in an epoch of star formation and galaxy evolution, a cosmically brief period when structure exists and complexity thrives. That makes this moment, this era, precious. And it reminds us that expansion is not just an abstract physical process. It shapes the universe's destiny, determines what's possible and what's not, sets the timeline for cosmic evolution from the Big Bang to the heat death. But let's step back from these vast futures and return to the present. There's something profound about knowing that the universe is expanding. It changes how we think about space, time, our place in the cosmos. It's worth taking a moment to reflect on what this knowledge means, what it tells us about existence itself. First, expansion gives the universe a history in a way that a static universe never could. If the universe was eternal and unchanging, if it had always looked essentially as it does now, then time would just be a parameter, a coordinate with no special significance. But in an expanding universe, time has direction. There's a past when things were different, closer together, denser, hotter. There's a present state. There's a future that will look different from now. This means the universe has aged. It was born 13.8 billion years ago in a state utterly unlike anything we see today, and it has evolved through distinct epochs, changing fundamentally as it expanded and cooled. We can trace this history, read it in the cosmic microwave background, see it in the distribution of galaxies, infer it from the abundances of elements. This historical dimension makes cosmology a science in the same way that geology or biology is a science. We're not just describing timeless laws, but tracing an actual sequence of events, a narrative of cosmic evolution. Expansion also means we're living in a special time. We exist during an era when stars are forming, when galaxies are rich with gas and dust, when the night sky is full of distant galaxies visible to our telescopes. We can see the cosmic microwave background, that direct remnant of the early universe. We can observe galaxies at many different distances and piece together how structure has evolved. In the far future, as we discussed, this won't be possible. They might have to work much harder, or might be completely unable to understand their universe's history. So we're fortunate. We exist in a cosmic era when the universe is comprehensible, when its past is written in the sky for those who know how to read it. That's a kind of privilege. There's also something humbling about expansion. It reminds us that we're part of a larger cosmic process, that the universe is not arranged for our convenience or centered on us. Every galaxy sees itself at the center of cosmic expansion in the sense that all other galaxies appear to recede from it. There's no special location, no privileged perspective. We're participants in a universe-wide phenomenon that operates without regard for human concerns. This perspective can be grounding in the best sense. The expansion of space won't affect your daily life. It won't change the distance between planets in our solar system or alter the orbit of the moon, but it's happening nonetheless, reshaping the cosmos on the largest scales, driving the universe toward futures we can barely imagine. And there's something poignant about the isolation that expansion brings. The galaxies we see in deep field images, those distant collections of billions of stars, are already beyond our cosmic event horizon. What's happening there now? We can never know. Any civilizations that might exist in those galaxies are forever isolated from us, not by cosmic law forbidding communication, but by the simple geometry of expanding space. This means the universe is larger and more full of structure than we can ever fully appreciate. There are realms beyond our observation, places we can never visit even in principle, galaxies whose light will never reach Earth, no matter how long we wait. Yet this limitation also suggests possibility. If there's more universe beyond what we can see, if the cosmos extends past our horizons, then perhaps it's infinite, or at least vastly larger than the observable portion. Perhaps there are regions with different properties, different histories, different outcomes of cosmic evolution. Expansion makes the universe a place of both connection and isolation. We're connected to cosmic history through the light that reaches us from the distant past. We're connected to the fundamental processes that drive the universe's evolution, but we're isolated from vast portions of the cosmos by the very expansion that makes it so interesting. There's also a philosophical dimension to expansion that's worth considering. In a static universe, space would be an absolute, unchanging stage on which events unfold. But in an expanding universe, space is dynamic, participatory, shaped by the matter and energy it contains. This aligns with the insights of general relativity, which taught us that space and time are not passive containers, but active participants in physical processes. Expansion is the most dramatic manifestation of this on cosmic scales. Space responds to its content by expanding, and that expansion in turn affects everything within space. This interconnectedness, this mutual influence between space and its contents, is a deeper truth about the nature of reality than the simpler picture of objects moving through unchanging space. Expansion taught us this truth. And finally, expansion reminds us that the universe is still becoming. It's not finished, not complete. Every moment, it grows larger, changes, evolves, structures, form, and dissolve. Stars are born and die. The whole cosmic system is in motion, not toward any particular goal or endpoint, but simply unfolding according to the laws of physics and the initial conditions set by the Big Bang. We're witnesses to this process. We're part of it. Our atoms were forged in ancient stars, scattered by supernova explosions, gathered into new solar systems. We're made of cosmos, temporary arrangements of matter that happen to be conscious, able to look out and understand the expanding universe that created us. That understanding, hard-won through centuries of observation and thought, is one of humanity's great achievements. We've learned to read the light from distant galaxies, to measure the expansion of space, to trace the universe's history from the Big Bang to the present, and project its future into timescales beyond imagination. And in understanding expansion, we've learned something fundamental about existence itself. That change is woven into the fabric of reality. That the cosmos is a dynamic, evolving system. That space itself is not static but alive with motion. This knowledge doesn't answer every question. We still don't know what dark energy is, why the expansion rate has the value it does, whether the universe is finite or infinite, what lies beyond our horizons. But it gives us a framework for asking these questions, a foundation for continued exploration. We live in an expanding universe, and that single fact shapes everything else we know about the cosmos. We've traveled a long way together through the landscape of cosmic expansion. We started with a simple question about what it means for the universe to expand, and we've seen how that question opens into layers of meaning, each more profound than the last. Expansion is not galaxies flying through space like debris from an explosion, though that's how we often picture it. It's space itself stretching, carrying galaxies along like raisins in rising bread, like dots on an inflating balloon. Every point in space sees expansion the same way, with distant objects receding at speeds proportional to their distance. There's no center, no edge, just a universe growing larger everywhere at once. We met Edwin Hubble and learned how patient observation revealed this expansion in the early 20th century. We saw how Henrietta Leavitt's work on Cepheid variables gave astronomers the tools to measure cosmic distances, how Vesto Slipher's redshift measurements hinted at something strange happening to distant galaxies, how Hubble put the pieces together and saw the linear relationship between distance and recession velocity that bears his name. That discovery transformed our understanding of the cosmos. It gave the universe a history, an age, a beginning in the Big Bang. It turned cosmology from speculation into science, grounded in observation and measurement. We explored how astronomers measure expansion through redshift, that stretching of light as it travels through expanding space. We learned about the Hubble constant and the ongoing effort to measure it precisely, about the tension between different measurement methods that suggests our understanding might still be incomplete. Then we encountered dark energy, that mysterious component that dominates the universe and drives accelerating expansion. We saw how its discovery in 1998 shocked the physics community, how it revealed that expansion is speeding up rather than slowing down. We explored the leading explanations, the cosmological constant and quintessence, and the deep theoretical problems that make dark energy one of the greatest mysteries in physics. We traced the history of expansion from cosmic inflation in the first instant after the Big Bang through the radiation-dominated era, the matter-dominated era, and into the current dark energy-dominated era. We saw how different forces have controlled cosmic evolution at different times, how the transition to accelerating expansion about 5 billion years ago marked a fundamental shift in the universe's trajectory. We contemplated the horizons that expansion creates, the limits to what we can observe and know. The particle horizon at 46.5 billion light-years marks the edge of the observable universe. The cosmic event horizon at about 16 billion light-years marks the boundary beyond which we can never receive information, no matter how long we wait. These horizons remind us that the universe is larger than what we can see, that there are fundamental limits to observation imposed by the finite speed of light and the expansion of space. And we looked into the far future, seeing how continued acceleration will gradually empty the night sky of distant galaxies, how the evidence for cosmic history will eventually be redshifted into invisibility, how the universe will become ever colder and emptier over timescales that dwarf the current cosmic age. Through all of this, one theme persists. The universe is not static. It's dynamic, evolving, becoming something new with every passing moment. Space itself has a kind of life to it, a capacity for change that shapes everything within it. This is perhaps the deepest lesson of cosmic expansion. We live in a universe where change is fundamental, where the very fabric of space responds to its contents and evolves over time. We're part of a cosmic story that began nearly 14 billion years ago and will continue into futures we can barely imagine. And we're living in a special epoch of that story, a time when the universe is rich with structure and light, when we can look out and see cosmic history spread across the sky. We can observe the cosmic microwave background, that ancient echo of the Big Bang. We can see galaxies at many distances and ages. We can measure expansion and infer the presence of dark energy. We can piece together how the cosmos has evolved and where it's headed. Future civilizations, if they exist, might not have these privileges. The expansion we're studying today might eventually erase its own evidence, leaving later observers in a darker, emptier universe with no way to learn their own cosmic origins. So there's a poignancy to our cosmic moment. We're here now, during this relatively brief period of cosmic history, when understanding is possible, when the universe reveals its nature to those who look carefully. That makes our observations, our measurements, our growing understanding all the more valuable. The expansion of space continues, as it has for nearly 14 billion years. Every second, galaxies beyond our local group grow a bit more distant. Every moment, space stretches. The universe becomes larger. This process will continue far into the future, reshaping the cosmos in ways both subtle and profound. We've learned to measure this expansion, to trace its history, to predict its future. We've uncovered mysteries like dark energy that challenge our understanding of fundamental physics. We've seen how expansion creates horizons and determines cosmic destinies. But perhaps most importantly, we've learned that the universe is not a static stage on which events unfold. It's a participant in its own story, space itself evolving and carrying everything along with it. This is the nature of the cosmos we inhabit, a growing universe, forever expanding into futures unknown. And as you drift off to sleep tonight, that expansion continues. Space stretches. Distant galaxies recede. The cosmos grows larger by imperceptible amounts, driven by forces we're still working to understand. It's happening now, has always been happening, will continue happening long after we're gone. There's a quiet beauty in that persistence, in the patient unfolding of cosmic expansion across billions of years. The universe asks nothing of us, but continues its growth regardless, indifferent yet magnificent. A process so vast it encompasses everything, yet so subtle we can only detect it through our most precise observations. If you've found value in this exploration of how space itself expands, if this journey through cosmic history and distant futures has resonated with you, I'd be grateful if you'd consider liking this video and subscribing to the channel. Your support helps me continue creating these long-form explorations of the cosmos, these attempts to make the universe's deepest mysteries both understandable and soothing. Thank you for traveling with me through the expanding universe. May you find peace in the vastness, wonder in the mystery, and rest in knowing that space itself is always in motion, always becoming something new. The cosmos continues its ancient expansion, carrying us all into futures we cannot know, but can, at least, imagine. Sleep well under the expanding sky.